Good morning. Now, this is the continuation of our class 3, that is the design of digital filters from analog filters, that is analog low pass filter design. So, in the last class, I hope you remember that we have studied about the design and specifications of Butterworth filter. Okay, now in this class, we'll finish up this topic, and here we will be discussing about the other two filters, that is Chebyshev filters and elliptic filters. Okay, their design and a brief specifications. Now, this is the name Chebyshev low pass filter. So there are two types of Chebyshev low pass filters, and both are based on Chebyshev polynomial that we will see now. They are categorized into two, that is type 1 Chebyshev low pass filter and type 2 Chebyshev low pass filter. In type 1 they have an all pole transfer function, that means they have only poles, that is they are constructed based on the evaluation of only poles and not zeros. It has an equiripple pass band and a monotonically decreasing stop band. So pass band has ripples, whereas stop band is drastically decreasing. Whereas in the case of type 2 Chebyshev filters, they have got both poles and zeros. At the same time, their pass band is monotonically decreasing, whereas the stop band has ripples, just the reverse of type 1. Okay, so their characteristics are just the opposite. Okay, so type 1 they have ripples in pass band, whereas stop band is drastically decreasing. In type 2 just the reverse, that is stop band has ripples, whereas the pass band is drastically decreasing. And type 1 has got only poles, whereas type 2 has got both poles and zeros. Now, by allowing some ripple in the pass band or stop band magnitude response, a Chebyshev filter can achieve a steeper pass to stop band transition region. That is, the transition from pass band to stop band can be made steeper. How? By allowing some ripples in pass band. That particular process is called by the name roll off, that is filter roll off, and this can be achieved by the same order Butterworth filter, that is um, acquiring of this process, that is roll off, is much easier in a Chebyshev filter when compared with that of a Butterworth filter of same order. Now, here you have to study a few expressions that are important while designing a Chebyshev filter. So, first we will deal with the terms or some specification parameters that you will have to evaluate while designing a type 1 Chebyshev filter. So, in type 1 Chebyshev filter, the transfer function, that is h of a s, this s is a complex variable, it is replaced by j omega. So the magnitude of this transfer function, this is called transfer function. So the magnitude of transfer function for a type 1 Chebyshev filter is given by this expression. Here there are a few terms. Tn is called Chebyshev polynomial, and it can have these two values depending upon the value of omega, where omega is called as the frequency. Okay, the omega p is called as pass band edge frequency. Okay, so when you see omega p, this is called, p stands for pass band edge frequency. Now omega s, this will be, that is omega, if it is like this, it will be stop band edge frequency, and if omega is written simply like that, it will be just an edge frequency. Okay, then epsilon, here in this term epsilon is there, this epsilon is termed as pass band ripple. Okay, so we have explained all the terms in the equation. Then this actually shows the magnitude versus normalized frequency graph of a type 1 Chebyshev filter for different values of n. N actually stands for the order of filter. Okay, so for filter, different order of filter, that is from n equal to 1 to n equal to 8, the response of this magnitude versus normalized frequency, or the response of the filter of various various orders shown in this graph. and that is the figure for three different values of filter of order n with the passband ripple. Here this epsilon, that is passband ripple, as I already said, is taken as 1 decibel. So from these plots it is seen that the square magnitude response, that is this one, square magnitude response, this is also called by the name transfer function, is equiripple between omega equal to 0 and omega equal to 1, that is in this region. It has got some ripples like this, whereas it decreases monotonically for all omega, that is for all normalized frequencies greater than 1. Okay, see, this is a normalized frequency or symbolic frequency, and for all these frequencies greater than 1 it is decreasing. So this sentence is well clear from this graph. So remember, omega p means pass band edge frequency, omega s stop band edge frequency, and simply omega means normalized frequency. Then what is epsilon? Pass band ripple. Now capital N, it is the order of the filter. So these are the terms. Now the order n of the transfer function is determined from the attenuation specification in the stop band at a particular frequency. For example, if normalized frequency omega, if it is equal to stop band edge frequency, then the magnitude is given by 1 by a. See the magnitude response expression, which is similar to that of a transfer function, as I already said before, is given by this expression. So you can write this one, and you can skip this. Instead you can directly write 1 by a square, that is the magnitude response for a type 1 Chebyshev filter is given by this one, and finally this step. And on solving we get the order of the filter n as this one. Okay, this you can write both these expressions. Here are the unknown terms are k and k1. What is k? It is called by the name selective parameter, and k1 is called discrimination parameter. So that's all about type 1. Now type 2 Chebyshev approximation or filter, the various specifications that becomes necessary while designing a type 2 Chebyshev filter is given here. Here it is also called by the name inverse Chebyshev response. Why? Because it exhibits a monotonic behavior in the pass band with a maximally flat response at normalized frequency omega equal to 0, and an equiripple behavior in the stop band, which is already explained while we were telling about the difference between type 1 and type 2 Chebyshev filters, right? Now here the magnitude response expression is given. There is a slight difference from type 1, and that is it is no longer an all pole function. That is, I have already said, that is type 2 has got both poles and zeros, as I already mentioned. Okay, so these are the main specifications that we have to study while designing a type 1 and type 2 filters. There are some expressions and the explanation of terms and their differences between type 1 and type 2 Chebyshev filters. Now this is just a graph that shows the magnitude and frequency response, as I already said. Now here there is an expression for amplitude characteristics. This is the expression for we have studied about the magnitude response. Now this is the expression for amplitude response of a Chebyshev filter. That is, it is expressed in in the general case, not mentioned about type 1, type 2. Generally, the amplitude response of a Chebyshev filter is explained or expressed by this expression. Here the unknown terms, which are the unknown terms, epsilon you know, it is the passband ripple. Cn, it is called a Chebyshev polynomial. And what about fc? It is the cutoff frequency. Now here you can see an f, that is sometimes called passband frequency in some cases, or generally the normalized frequency. So here you can write this f as normalized frequency. Okay, fc cutoff frequency. Now this Chebyshev polynomial, that is Cn, that is shown in this equation 1. Now the Cn can have two different values, that is Cn, it can be either expressed as this or it can be either repressed as this, depending upon certain condition. That is in the case of this one, this actually stands for the expression for Chebyshev polynomial Cn in pass band, and this one actually stands for the expression for Chebyshev polynomial in stop band. Okay, these are the expressions. That is, one is expressed in a cosine function, whereas the other one is expressed in a hyperbolic cosine function, and h is there, right? And then it's a limit, which is also given. So this Chebyshev polynomial Cn is different for passband and stopband, and their expressions are given by this. Okay, now from examination of equation 2 shows that in the passband, the Chebyshev polynomial will have values between -1 and 1. As a result, we can conclude from 1 that in the passband, the expression for the ripple, that is epsilon, is given by this. That is, this amplitude response is less than or equal to 1 by 1 plus epsilon square and less than or equal to 1. That is the limit of this amplitude response. Its value lies between 1 by 1 plus epsilon square and 1. Now, that is, the above is the magnitude of ripple in passband. Okay. Now the lower bound. Now another expression is a ripple specification, that is in terms this epsilon, we know epsilon is actually the ripple in pass band. Okay, now in the case of that is in the case of this one, that is in the ripple specification gp, we can write this ripple in pass band epsilon as this expression. Okay, so I will explain once again. This one you have to draw this graph, then just keep all this and write the expression for amplitude response. This one, explain each of these terms as I have already told. Then what will be the value of Cn for pass band and stop band. Then the amplitude response value, it lies between this and this. And finally, in terms of ripple specification, the ripple the ripple in pass band epsilon square is given by this expression. Okay, then next we are going to substitute the filter specifications at Fs and Fp. That is, we are using Fp instead of Fc, and then by using equation 5 in 1. That is, after writing this, you have to write substituting equation 5 in 1 and then replacing Fp for Fc, we get this expression, that is 10 of raised to gs by 10 equal to 1 by this expression, and finally solving we get an expression for this n as this. This equation is important. Okay, this will be epsilon square plus 1 will be equal to 10 e raised to minus gp by 10. Okay, so either you can skip this expression and just write substituting equation 5 in 1 and using Fp for Fc, we get the expression for n as this, and you can directly go to this expression if it is difficult for you to study this. Okay, this expression for n, that is order of the filter, is important. Okay, because it comes in various calculations, because this is how we design or we decide the order of a filter, that is which type of order that of filter that we are going to design. Now based on this formula, there is an example question, a problem. No need of studying this problem, just I am specifying, that is if a question is like this, how we will find the order of the filter. So that's why I told this expression is important, order. So you have to write this expression, study this expression. Okay, see the specifications, everything is given, and you know the formula for n, and that is, which is that this particular formula, n. So write that formula and substitute the values given in the question. So you will get the value of n as 2.593. As said, this cannot be in decimals, it should be an integer. So what is that? The integer nearest to 2.593, it is 3. Okay, so the order of the filter required is 3, but in order to decrease the ripple in the pass band, so here we got the order as 3. Okay, that is there. Then another expression, we have to find the value of epsilon square, whose formula is already discussed, and its value is equal to 10 raised to minus GP. It is there in the formula above. Here, instead of in GP, what is the value given in the question? It is 1. So in order to reduce the ripple, we are actually decreasing the value of G. That is, we are making it is half. So 1 by 2, it will be 0.5. So we are substituting, instead of 1, we substitute 0.5 and we get the value as 0.1220. And finally, we evaluate the amplitude response GF square by substituting all these values. So this is how you solve a problem when you are given the specifications of a Chebyshev filter. No need of studying this problem, just go through it. Okay. So that's all about Chebyshev filters. And it is seen that, just a theory part, Chebyshev filters, as I already said, it has the advantage that a lower order polynomial, that is, if we are to design a filter, a Chebyshev filter of lower order will satisfy our criteria very easily, even with using a Butterworth filter of higher order. But Butterworth filter has more linear characteristics when compared to Chebyshev filter. That's the only drawback. Now the last session, elliptic low-pass filter design. It is known as Gore filter. It has got equiripple, that is ripple in passband and an ripple stop band magnitude response. That is, ripple is there both in passband and stop band. Here the transfer function meets a given set of filter specifications, that is passband edge frequency omega p, and then omega s, that is stop band edge frequency, and so on. And a minimum stop band attenuation A, that is, in the last sessions we have come across a capital letter A, right? That is called minimum stop band attenuation, and N that we have known, it is actually the filter order. Okay, that is now in the case of elliptic low pass filter design, the square magnitude response, as in the case of Chebyshev filter, is given by a different expression. See here, instead of Tn, it is Rn. That is another polynomial, or it is a function of order n which satisfies a particular property given by this. Now its limit actually lies between 0 and 1, that is normalized frequency lies between 0 and 1, and that is, the roots of the numerator lies between 0 and 1, whereas roots of denominator lies between 0 and infinity. What is omega? Normalized frequency. So that is, while designing an elliptic filter design, you have to study the expression for this magnitude response, that is this particular expression. Okay, square magnitude response. Now another expression for the order of the filter, capital N is given by this. Here, as already mentioned, K1 is the discrimination parameter, and now K dash is the selective, K is the selective parameter and K dash is the discrimination parameter. So there are expressions for capital order N, capital order of filter N, then K dash. What is K dash? Discrimination parameter. What is K? Selective parameter. Then expression for row 0 and row. Okay, so these expressions will be useful while designing a elliptic filter, and we will see this in a problem very coming soon. This is a magnitude versus normalized frequency response of an elliptic filter. Now this is the problem. You are given, no need of studying, just go through it. If you are given a question, you can solve how. Okay, you are asked to determine the order of the filter, that is capital N, and you are given some filter specifications. That is, you are asked to design a elliptic filter with these specifications, which are the K selective parameters given as 1 by 5, that is 0.2, whereas the discrimination parameter K1 is given as this particular value. So first, what will you do? Equation 3, you know. Okay, you are given K, that is K is 0.2, so substitute and you will get the value of K dash. Okay, now use this value of K dash in equation 4, this one, so you will get the value of rho 0, this one. Now use this value of rho 0 in the expression 5 that is given above. All these expressions are numbered as above. Okay, 5, then you will get the value of rho. Now you have got everything, and finally, so use the value of 1 by K1 and rho in the final expression for order of the filter, which is already given in equation 2, this one. and this is how you get the order of the filter if you are given some specifications. Only in the case of elliptic filter it is 2.2, it cannot be a decimal, it has to be integer. So the integer nearest to 2.2 we can write it as 3. So 3 is the order of the filter. Now there are some programs for designing analog elliptic filter, and that program name is called analpf or zpel. That is something like that. See, programming. No need of studying all this, just note down the name. These are the two programs that we use. They are mainly based on the poles and zeros of the filter, because in elliptic filter they are designed using both poles and zeros. And once you achieve the poles and zeros necessary for designing an elliptic filter, we translate this into a Sislin one. Sislin one means, and using the help of board plot. Board plot means it is just a graph like this. Magnitude and frequency versus graph. We draw the board plot, and then we use the transfer functions and all to make the particular design. So no need of studying all this, just mention the name of these programs. Okay. So that's all about this analog low pass filter design, that is Butterworth, Chebyshev and Elliptic. Now in the next class we will discuss about another new topic of this module. Okay, that's all for now. Thank you.